Hello and welcome to Calculus Video 1, an introduction to calculus. My main goal for this video is just to introduce you to the two main topics that we'll have in calculus. One of those is the derivative, the second is the integral. We'll spend about the first maybe 3/4 of the semester talking about derivatives. What is it? How can we use it? What are the different formulas for derivatives? What are some of its applications? And we'll spend about the last quarter of the semester talking about integrals, its uses, formulas, and applications. So first, derivatives. There's two ways we can think about a derivative. One way is the slope of the tangent line at a point on a curve. Right? So if you're thinking about a curve, picture a point somewhere on the curve. The slope of the tangent line at that point of the curve, that's one concept of the derivative. In fact, if I kind of scroll down here, a picture of that might look something like this, right? We have an XY axis, a nice little curve here, kind of looks like this. This is like our function. We pick some point, say here, on the curve. A tangent line is a line, a straight line that touches that point on the curve at just that one particular point in its neighborhood. So, something kind of, I can draw decently. Yeah, I kind of missed. That's supposed to touch the point there. Just make the line thicker. There we go. It's that tangent line that touches the point on the curve. The slope of that line, often we represent slope as m. The slope of that line is one idea, one way to explain what a derivative is. It's the slope of the tangent line on a particular point on the curve. A second way to kind of explain what a derivative is, it's the change of the y value, or the change of the function value, as the x value changes just a small amount. The change of the y value, or function value, as x changes by a small amount. And while those two explanations might not seem the same, they really are. If you consider this change of the x value as a very small amount, those two explanations really are the same. For example, if I come down here and I look at this curve, the slope of the tangent line, right, has like a change of y over a change of x. If we look at the curve itself, right, as opposed to the tangent line, the change of y over change of x might look like this. This is the change of x, this is the change of y, and you might be saying, well, those two things are not the same. Well, they're not the same because I can't draw my change of x any smaller. But if you were to zoom in, right, picture the curve of f there, and you want to zoom in closer and closer and closer and closer at that point that we picked, as you zoom in closer, even though that curve is in fact curved, the closer you get, the more of a straight line that looks like, right? And so if we zoom in really far, that curve zoomed in is actually a straight line. And the tangent line then would line up exactly where that straight line portion of the curve is, and the change of y over change of x, the small change in y over this small, well, the change in y over the small change in x, would be the same as the slope of the tangent line. Right? And so the slope of the tangent line, maybe a better way to write this is about the same thing as change of y over change of x. How much does the y value change given a small change of x? And then what we do is we say, okay, the triangle there means change in. We need a way to designate small change in. And so instead of the triangle, which is called delta, we use the first letter of delta, d, and say dy, as in change of y, small change of y. That's what the d there means, small change in over small change in x. What is that small change in y given a small change in x? If you zoom in, that ends up being the same thing as the slope of the tangent line. That's the idea of a derivative. Integral. The idea of an integral 1 is what we consider to be the antiderivative. So in other words, we have this derivative, which we're not sure yet how to find it. But if we undo that, that's called the antiderivative. That's what we consider one way we talk about the integral, as the antiderivative. The second way seems very different, and it really is different, although we use the same symbolism, or at least close to the same symbolism for it. It is an infinite sum of small areas. And what we're going to do here, this is towards the very end of the semester, is we are going to take a curve, say here, f, on a particular interval from a to b, so if x values go from a to b, that creates this sort of shape here. And what we want to do is find the area under that curve. What we're going to do is we're going to create, say, little rectangles from there. These are these small areas, right? And what we're going to do is we're going to add those small areas together. That idea of summing together a bunch of small areas to become the integral. Except there's one thing here, we're going to take those small areas, we're going to make them even smaller. We want to add an infinite sum. We want these areas becoming smaller and smaller and smaller, which creates more and more and more of them. That increases our accuracy until we actually get the area under the curve. We end up losing all of the error that we would have. You see kind of the error here with my rectangles. We missed a little bit up here, we missed a little bit right up here. Right? The more rectangles you have, the less area you have. If you have infinitely many rectangles, you don't have any area. And you get the area under the curve. So that idea of summing an infinite sum of small areas is another way we can use the integral. So really that's calculus in a nutshell. We have derivatives, the slope of the tangent line at a point on a curve, or the change of the y value or the function value as x changes by a small amount. And then we have the integrals, which is the antiderivative, undoing the derivative, and also an infinite sum of small areas. And finally, I'll say one more thing. Both of those concepts that we're going to do, derivatives and integrals, rely on a concept called limits. So while limits isn't one of the two main topics in calculus, we can't do the two main topics unless we first understand limits. And what a limit is similar to what we've just been talking about summing up small values or one value approaching another value. We would say limit, of a basic definition here. It's the value of y, or the value of f of x, so the y value or some function value, as x approaches a specific number or specific value. As x approaches, that's an O, approaches a specific value. Right? In other words, as x approaches 0, what happens to the function value? What does the function value approach? That's what we're limiting to. What is the y value, the function value approaching as x goes to 0? It doesn't have to be 0 as x goes to 1. what does the function value approach? As x goes to infinity, what does the function value approach? These are the ideas of the limit. What is happening to the y value, the function value, as x approaches a specific value. And it turns out we don't actually care what happens at 0. We don't care what happens at 1 or at infinity, if you could ever be at infinity. We really only care what happens to the function value as x gets close to 0, as x gets close to 1, as x gets close to infinity. That's the idea of a limit.